For this stereochemistry review, we will start by drawing a Fischer projection of this chiral tetrahedral carbon. So when you draw a Fischer projection, the idea is to rotate the molecule so that you can make a backbone, and then their horizontal pieces will be coming out towards you. For a lot of students, this is easier to do with the model kit. But what I'm going to do is take this OH and put it at the top, and I'm going to take this ethyl group and put it at the bottom. So what I'm doing is taking this molecule and really just kind of turning it this way so that the Br is on the left and the H is on the right. So now I can assign my R and my S, and although the question didn't ask for it, I'm going to assign it anyway. Bromine is going to get a 1 because it's heavier than oxygen, which is going to be my 2. They're my heteroatoms. That makes this the 3, the ethyl group, and then I'm going to turn in a clockwise fashion. Because H is on the horizontal, turning clockwise means this is an S orientation. For number 2, to assign the R and the S, first we look for our heteroatoms. We have bromine and chlorine as our heteroatoms. Bromine is heavier than chlorine, so that's the order they're going to go in with ethyl here. This rotates in a clockwise fashion, but the H is coming out towards us. Because the H is coming out towards us, this is an S configuration. Note on the Fischer projection, our horizontal pieces are coming out towards us, so we're really doing the same thing. You see the H is coming out towards us, so the clockwise direction is an S. For number 2B, we have our heteroatom, which gets 1. We have a C that gets, or a CH2, which has a higher priority than CH3. H is coming out towards us. We are rotating counterclockwise. Since H is coming out towards us, this is an R configuration. For number 3, we are going to identify identical enantiomer or diastereomer. So what we have here, well, it looks like we're going to have to assign R and S. So I'm going to start with this asymmetric center. N gets 1 because it's a heteroatom. The majority of the rest of the molecule gets a 2. Methyl gets a 3. H is on the vertical. I'm turning clockwise with H on the vertical. That means this is an R. For this stereocenter, we have bromine, which is going to be our 1 priority. The rest of the molecule is 2. Methyl is 3. We are turning counterclockwise with H on the vertical, so that makes this an S. Here, the bromine asymmetric center. Bromine is 1, rest of the molecule is 2. Methyl is 3. We are turning clockwise. H is on the horizontal. So because this is clockwise, H on the horizontal, we have an S configuration. For the next asymmetric center, we have nitrogen is 1. The rest of the molecule is 2. Methyl group is 3. We are turning clockwise. H is on the horizontal. This is an S. Now, even though the bromine is here, so the bromine stays the same, these asymmetric centers have changed. We have 2 asymmetric centers. They are not direct opposites of one another. They are also not the same. That means these are diastereomers. Number 4, we're going to calculate some specific rotation. Now, this is directly related to our lab, and you did these, or you should have done these calculations with the lab. The equation is that the specific rotation is equal to the observed rotation over the concentration times the length of the cell path. So the concentration will be in grams per milliliter, and that's convenient because we're given grams and milliliters. And the cell path should be in decimeters. Well, 10 centimeters is 1 decimeter. So we can convert this and calculate. So our specific rotation for compound A is going to be 35.0 over the concentration should be in grams per milliliter times the cell path length, which we're going to take as 1. Now, because this was a positive rotation in the positive direction, our specific rotation is also going to be positive, and this works out to 350 degrees for A. So for B, we will calculate the observed rotation in a similar manner, but this time we're given the specific rotation. So we put the positive 176.0 on the left side of the equation. We're calculating the alpha in the numerator. We have our concentration of 0.250 grams per 1 milliliter here. And the path length this time is 5 centimeters. Well, 5 centimeters is half of a decimeter because a decimeter is 10 centimeters. So to do this calculation, I'm going to multiply both sides by the denominator. Now, if you're watching this in Module 2, you can stop here because 5, 6, and 7 really should be review for the final exam. We'll go over addition reactions in Module 7. Now, in number 5, how many stereoisomers can we produce? Well, the addition of bromine across a double bond or across a pi bond will yield an anti-only product. But there are two ways we can form that anti-only product. We can have bromine up here and bromine down here, or we can push it differently, but it's going to be trans either way. So we can form with the bromine coming out and the hydrogen coming out here. And we might be able to punctuate this by assigning our R's and S's. So bromine is 1, rest of the molecule is 2, the methyl group is 3. We are turning counterclockwise. This is an S configuration at this stereocenter. And over here we have bromine is 1, the rest of the molecule is 2, and then the ethyl group is 3. That is a counterclockwise, but H is coming out towards us, so this is an R configuration. Now we can also form the other trans isomer with bromine coming out here, but receding on this asymmetric center. So that makes the hydrogen pop out and the hydrogen recede here. So when we assign the R and the S to these, over here we have bromine, the rest of the molecule in the ethyl group. Now we are turning counterclockwise and H is receding. So that makes this an S stereocenter. And here bromine is 1, the rest of the molecule is 2, the methyl group is 3, H is coming out towards us. We are turning counterclockwise, but H is coming out towards us, so this is an R. Now these are not identical. We can't just turn the molecule around on this axis or anything. These are an enantiomeric pair of stereoisomers. So when you have this bromine addition across a double bond, you form an enantiomeric pair. Now for number 6, we have hydrogenation with a palladium catalyst. This adds syn only. That means our addition of hydrogen is only going to occur on the same side whenever it occurs. So when we do this, so our hydrogen comes out over here, then our hydrogen is going to come out over here as well. Similarly, we can form the receding hydrogen enantiomer, and these are enantiomers here. Let's name the stereocenters just to be sure. So basically the rest of the molecule is 1, this ethyl group is 2, the methyl group is 3. We turn counterclockwise, but the H is coming out towards us. So that means this is an R configuration on this side. Over here, we have the rest of the molecule is 1, ethyl is 2, methyl is 3. We are turning counterclockwise again. H is coming out towards us, so this is an R configuration at this asymmetric center. Over here, we have the rest of the molecule, the ethyl group, the methyl group. We are turning counterclockwise, but this time the H is receding. That makes this an S configuration. And over here, we have the rest of the molecule, ethyl and methyl, 1, 2, 3. We turn then counterclockwise, H is receding. That makes this an S. Notice how this is an enantiomeric pair. It's an enantiomeric pair. We started with an achiral compound, we end with an achiral mixture. This is a racemic mixture, therefore it shouldn't be optically active because we should have a 50-50 split for both of them. So for 7, again, we have a syn addition. It's the hydrogenation with a palladium catalyst. This time, though, we are starting with a a chiral material, we need to end with a chiral material or with a chiral mixture. And the answer really lies in this stereocenter here. So although we can add the hydrogens coming out towards us, or we can add the hydrogens both receding, what we end up forming then is a diastereomeric pair of isomers in this case.